Hello everyone, thanks for dropping in. My name is Ryan Delucchi.
And I'm Sergei Shabanau.
Today we're going to be talking about pretty parsing. So at the most fundamental level, we're actually discussing building parsers with functions. And by that I mean, as a basis of pure functional programming, we use functions as the fundamental building blocks for building parsers. And that requires, of course, that these functions must be composable, so they must be total and referentially transparent. And just as a quick recap, I would say by total I mean that they're defined for all input, means no throwing of exceptions. And referential transparency would be, there's two different definitions. I like substitution by construction. I like to use a by construction definition where we say that regardless of context, given any input, the function will return the same result given that input and not have any side effects. So specifically, we will be looking at invertible parsers, which is, it's actually a relatively new technique for constructing parsers outlined in paper illustrated right here from these folks at Marburg, University of Marburg in Germany. And I strongly encourage folks to take a look at this paper. It's quite fascinating. It illustrates an implementation of invertible parsers using Haskell. Now, we're actually going to be talking about implementation that both Sergei and myself have been working on, which is actually the scalaz-parsers project, which started last year as a part of the Scalaz open source mentorship program that John DeGoes organized, and yeah, so to be perfectly clear, this is a pure implementation of invertible parsers from the ground up. So here's the reason behind invertible parsers. It's about looking at the fact that when you want to write a parser of, say, it's like for a scripting language or a configuration language of any kind, for anything that you need to build a parser for, oftentimes we need to be able to build, not only build the actual parser itself, but also a way to print the content of the code in a nicely formatted format. And that's the idea behind invertible parsers, in that we actually have a means for having the implementation of both the parser and the pre-printer in a single cohesive, seamless design. And that reduces redundancy, which is kind of the whole idea, because there's actually a lot of commonality if you were to write these out separately, that this saves you if you actually use a more cohesive design, which invertible parsers has. Now, we're going to be talking about, first I'm going to be explaining about isomorphism within the context of actually comparing it with partial isomorphism. So for those who've attended the workshop earlier in the conference, that'll be useful to reference that as Alex actually went into more detail on defining isomorphism. But here we'll be mostly look at, I'll give a brief definition for folks that may have not attended that, and explain in comparison with partial isomorphism, which is central to the concept of invertible parsers. So we're going to do a simple definition given two functions, f and g, where the domain of f corresponds with the codomain of g, and the domain of the codomain of f corresponds with the domain of g. And we're going to say if they're isomorphic, then if you compose g with f, you get the identity function on A. Or if you compose f with g, you get the identity function on B. So you have a correspondence going both directions on both of these functions. A complete correspondence there. And compared with partial isomorphism, we have, if you take subsets of A and B, we'll call it A prime and B prime respectively, let's say that these subsets are congruent with each other, meaning they're isomorphic. So that's actually isomorphism right there. But to make it partially isomorphism, partially isomorphic, we have to say that, okay, for all x in A, set subtracting A prime, so everything that's not an A prime, then f is not defined at x. So we know that there's holes in the definition there. Also going the other direction, there might be there as well, where you say for all x and b with b prime subtracted, set subtracted, g is not defined for x. And this is actually expressed in Scala in this fashion. Now we're sort of bending the definition a little bit in the sense that we're saying that the functions are not defined if you receive none. Normally you don't follow that definition because, I mean, these are total functions after all. But for our purposes here, it makes sense because when partial isomorphism becomes a top-level concept with invertible parsers. So, and this is an illustration of why that's the case. Because for any given input, there exists an input that there may not be a way to print the result. For a given input, there may not be a way to parse it. That's why partial isomorphism becomes important.
Thank you, Ryan. Before I'll show you the library itself, what I'd like to develop is a bit of intuition what exactly invertibility means in terms of parsers. So when we're talking about parsing, what usually comes to mind is some kind of parsing textual representation of, let's say, this binary number into a typeful value. And printing is simply going back. So invertibility essentially is a property of a program that can be run in both directions. So it's a single program that you can use to go there and back. And our library is in fact very generic. We are not doing anything with concrete types. We just allow users to define inputs and outputs. And if you look at invertibility from generally, then there are many use cases that are also possible to implement with the same library, with the same code. So this, for example, shows a way to take some bytes and convert them into an HTTP request. And now the other way back is essentially taking a request and going back to bytes. So this gives you a client and a server in one implementation. One program essentially implements both. So now let's see how this is done in library design. So that's the summary of abstractions that library provides. And the way to read it is essentially we have this parsing trait. The whole purpose of it is to capture types. Our parsing is effectful, so we have effect types. And then we have two abstractions available inside once the parsing is instantiated. Those are equiv and codec. So the purpose of equiv is essentially to capture mapping functions. So all parsing loosely reminds of isomorphisms. So if types of input and output are defined by users, then these functions are also defined by users. And equiv is a construct that captures these functions. Once the functions are captured, provided by user, what library gives back are constructions called codecs. And those are real runnable programs. So this one just reminds you of what types we have. And we have 5 types here. What we try to do is use path-dependent types in order to remove this whole clutter of inference and make function definitions way simpler. So what's inside the library machinery? Essentially, it gives you access to codec and equiv abstractions. And once you instantiate it, you have access to all predefined combinators, to a syntax of functions where you can compose codecs and equives and build on top of them. And we also have something that is, it's a way to extend the library. So it's not abusive, but I'll show it what it is later. So parsing is essentially built on the foundation of isomorphisms. In scalaz there is an isomorphism definition, and it's a mapping that goes from A to B. But the paper itself that talks about invertible parsers, it provides a different abstraction, which is called partial isomorphism. The reason for that is parsing is kind of function that may not succeed. And as Ryan described before, in Scala it's used with wrapping the output type as an option. What we have is a little bit more complicated use case. We want to make parsing effectful. And for that reason, we use an abstraction called equiv. And this design was provided by John about a year ago. So essentially, equiv is his idea. Thank you. So equiv is a loser abstraction. So what it does, it essentially gives you some mapping or choice that you can make given an A, you can make a choice of B. But only if there is some mapping that exists between A's and B's. And it captures two functions as isomorphism do to go to the opposite direction. Now, it's not an isomorphism because identity law here obviously don't hold. I'd like to point out that these types are defined very generically. So it's actually an arrow composition, not a function composition. And scalaz, for example, it defines a type alias that can be used for a function composition. What we essentially had some time ago is a definition of equiv, which is used with arrows. But our implementation at this moment has a definition of equiv with a function. So this is really a practical solution here. However, nothing prevents us from using arrows. So the way to work with the library is by user gives us functions, we give back codecs. The way these functions are composed is powered by the abstraction called category. So this is new in scalaz 8. We essentially use this code inside the library. And again, it's very generic. It's defined on arrows, not on functions. So what we have is we have provide implicit instances for construction of parsing. And these categories are just, they exist, the instances exist in the library. However, with just categories, not much you can do. So practically what we also require are instances of applicative for both effects F and G. And it's easy to see that if we define categories this way and we have functors for F and G, then essentially we have a Kleisli category. Now these functions that you give to equiv instances, they are monadic functions. Right? And what the machinery that used under the hood is Kleisli composition. Now to prove it, we can even instantiate the library with just monad. And what we have to do under the hood is we derive instances of categories for them. And I had to mention that we also have an error type to capture precise errors. And the whole truth is that we need applicative error for instantiating the parsing library. And you can do it with monad errors as well. So now I want to show you a real example of how to use the library. It's a true example, but it will show how this thing can be used in practice. And what we're going to do is we will really parse this 101 value. To do it, we'll just instantiate some output type, or define. And its type is two inhabitants, 1 and 0. And then we fix our types. Our types, let's just put error to unit, because we don't care for this demo for now. And then our effect would be an error or A, some value that is produced. And after that, you can instantiate the parsing itself, and all the instances, as I said, would be provided implicitly. And then last thing to do is actually start using it, define a grammar. With grammar, what grammar is it's a set of codecs. And how to read this? The way to read it is really sequentially. What you do as a user, you give your functions to construct equivalence instances. Then you use equivalence instances to map over existing codecs and create new codecs. And then you can compose codecs together. It's really simple flow. Well, you have to start with something that initially is a codec. So let's say this one takes a string as an input and takes a character out of it. And then you provide mapping functions. You lift them into equivalence instances, and then you use them to create more codecs. Finally, you combine them, and what's in fact similar here is that you can use, in order to parse 101, you actually have a codec that looks as 101. And type inference works. Even IntelliJ is capable of inferences if you need to ascribe types. Now, that is the runnable thing. All the codecs are runnable. You can run them in both directions. If you give them string, it will give you output. If you give them wrong string, it will give you an error, so you'll get the left side of an ISO. And this can be extended further. So essentially, you just build on top of these codecs more and more. Here, if let's say you have a way to map 0 or 1 into a binary, which you obviously have, you can use it to build a different codec, which now takes more zeros and ones as an input and outputs a list of them. And this also runs in both directions.
All right, so now we're going to throw up the hood and drill down into some of the lower level definitions behind these codecs and equiv combinators. And you'll see we'll start with a digit codec here, which is based off of the one that Sergei was talking about here, where we're actually parsing a single digit. And you'll see we start with the char codec, which is composed with the ensure combinator that, given a predicate, which it has a sort of a promise saying that, okay, this needs to be a digit, and an error condition if that fails the check. So let's look at a quick definition of the types, because we're actually going to be using this parsing context up here. So the parse effect here is going to be a sum type of either the error condition on the left side and on the right side the actual parse result. And that is, we have the print effect in G, and that's the same sum type there. And we have the error type as well, which could be a string. Now let's take a look at the char codec definition. Pardon me, I alternate between saying char or char. I'm saying the same thing. So from the context, we actually define a codec by using a liftf, doing a liftf, using the liftf combinator, and that allows us to lift this function that takes a character off, and of course if it's empty, that's an error condition. Otherwise, we have the character as a result from the codec. And then we have the equiv combinator ensure, as I was explaining. Now let's look at the implementation of that. Now you see that's the signature, where we're passing an error into it and a predicate. And the equiv type is quite interesting here because it's completely symmetric. It's of type A and A. And the idea behind that is once again, that's added as a guarantee, saying that, okay, it's going to satisfy this predicate. Otherwise, we raise an error. And as you see, these are the arguments right here. And the predicate is bidirectional. So whether you're in the parse direction, you would use the same predicate as you would if you're going in the printing direction. However, it's asymmetric here in the sense that depending on your effect, how exactly we're lifting the parse or print result depends on the effect. Same for how we raise errors as well. So that's an important thing to note there. So now let's take a look. We're going to continue our deep dive and take a look at the lift combinator. Now, once we look here, we start to see at our lower layer of combinators, we actually start to see profunctor combinators. And the lift operation is where we begin to see that, because we're actually doing an IMAP right here off of identity. As you'd expect, identity would also be an equivalency between A and A. We're lifting both of these functions, AB identity and BA identity. Those are actually profunctors right there. I'll be showing the definition in a second here. And we're calling the IMAP method right here, which, once again, is off of the context, the parsing context, which you'll notice, you'll see, we've shown this same kind projection before, and it follows this shape as from AFB, and then BGA, so it follows the same shape there. And the idea being is that we're actually making use of these two operations, which is map first and map second, whereas map first is actually a profunctor contramap operation on A, right? And then we have the second one, map second, which is actually a functor map operation on B. So using IMAP, we can effectively lift these two functions, BC, CB, which they're, as you can see, they're going both directions, and lift them into an equivalency from A to C. So now I'm going to show an interesting refactoring exercise. Now that this looks pretty crazy, I know, but it's okay. We don't have to see all this, split all the components here right away. But as you can see, that's a conjunction definition, which all it is we're saying we go A, B, C, D. We're resulting in an A and C implies B and D. So what's quite interesting is, even though that these profunctors are bidirectional by nature, we can still do algebraic manipulation on these profunctors and simplify this dramatically. And I'll show you how we went about this. Let's first take a look at compose x7, x6. You'll notice I'm using the compose operator right here. That maps, that's just an alias for the compose name there. So that expands to swap and drop first. And then, of course, we have swap 2. Well, that's highlighted because, guess what? When we expand further to x5, we see swap and drop first again. So, okay, this seems like something special about this operation, so we can actually expand this out into a new function that we intuitively name curl. Yeah, okay. So curl, which takes some third x type, conjunction with A and B, and then gives us B and A. So that's a swap and drop first. So when you do that, you actually simplify the operation right there. So now you have curl swap 2, which, as you can see in itself, there's 2 of those. So we could probably factor that out as well. We ended up deciding to leave it, but that's another, this could be even expanded to a separate operation too. But let's expand further though. And when we expand further, we see that there's this combined swap first, second. And, well, we can tell that this looks like a useful operation. It seems to be sort of like a closing operation for the entire conjunction that we're computing. So we expand that and we call it cross. So you have A implies B, C implies D, and that actually, as you can see, a return type on this is A and C implies C and B, A and D, all right? And the end result, and see we actually do a substitution right here, and And the end result is, I mean, remember before we had the long, complicated conjunction definition. Now we have something that has some symmetry to it. It's rather elegant, I would say. And you know, it's more easily to read. So there's my deep dive.
Thank you. Yeah, it was a deep dive. We lost like a half of the audience, I think. Let's go back to the surface for our simple parser, which just parses numbers into typed numbers. So interesting thing here that you see is there are a lot of libraries out there. They all do parsing. Now, how scalaz is different? So I picked two which are quite known. One of them is DETOUR. It uses monadic composition. And fast parser is a very highly optimized thing. So if I want to do the same simple parser in these three libraries, and that's how they look like in my remote works. So the code for DETOUR and fast parse essentially is smaller than scalaz. And you might be wondering, what did you guys do here that the code is so big? Now it's big indeed, but the way to look at it is probably from the opposite. What's interesting to see is what we actually have in common. And there are some things that you must do with any parser. So one thing is extract your character. Oops, this one. And it's the same everywhere. There is no invention and it must be done. The other thing is mapping a character into a typeful value. And it also must be done, and this is exactly the same everywhere. And the last thing is composition of extractors, or codecs if we follow our names. And it's also done exactly the same. We didn't even invent syntax, symbolic operations for syntax. They stay the same. Now what's different is the features that library does on top of its counterparts. So we have this error type, here we have effects, and we have invertibility itself. And that's where the extra code is coming from, and that's what it's used for. So I'd just like to give you a quick example of what it has to do to make a parser one way. So this is the amount of code to just parse these simple strings. And assuming our library goes one way. But now in order to go two ways, it's just that. So the point here is that going two ways, if needed, only takes a little bit of extra of code. And this code is type safe. You don't need to repeat all this machinery again. You just have it right away in a single application. About error types, so we have this type fixed to unit, and obviously if you give something that isn't parsable, it's not interesting, it returns you left of unit. But here we can specify errors precisely. We have an error type. And unlike other libraries that use messages that are baked into the code, what you can do is you can annotate all your combinators that don't return values at some point with precise error messages, the way you like them to be. And you can use it in French. Even add a translation file, although that's not going to be referentially transparent, so I'm not recommending it. And now, if you change effects, you can even use monotransformer stack to do something useful, say collect all the messages. Or you can use I/O and do some effectual manipulations inside the parser, because everything now composes together. So one thing we didn't cover is exactly what is this codec. So the mapping functions, we get used to build them. But what is codec here is, it's our way to compromise. So essentially, codec is a runnable parser. It's something that is produced by library and you can use it. But it's sort of also a choice we made for users. We actually didn't make any other choices except for this one. And the way to understand it is essentially in the signature. So if codec, sorry, how's that? So if codec is a program that takes A and returns B, then there is something in its definition is the output type A. And this A is easy to guess that it's just an unparsed input. So parsers are special cases of functions. They don't essentially consume all the input. They take a portion of an input and keep the rest for the next invocation of that function. So if you look at equivalence relationships, they are chainable functions. Their input and output changes. But codecs are composed differently. Codec input never changes, only output changes. And essentially what codec is, it's this bridge between functions that are produced, that consumes input completely, and functions that consumes only a portion of this input. And this is what library does. It converts functions, one kind of functions, into a specific kind of functions that are useful in parsers. Now, why did I say it's a compromise and a choice? That's because if you need to implement any kind of parsing library, what you have to do is essentially build 3 different constructs. It's a sequence operation where you consume a portion of input and another part and so on. It's a union where you need to map an input into some value, but if it doesn't work, then you try another one. And mapping. So for mapping, we have equivalence here, but first two, library, the paper itself, a foundational paper, uses specific type classes. We have scalaz, so we don't need to invent those type classes or implement them again. But codec is what implements those classes in our library. We still need to provide instances for them. And that's what codec does. And it does this with this specific unnamed feature that we call parser operations. Essentially, that's a trait that contains all the needful operation there that has to be done. Okay. So I showed you, as usual in these presentations, we have some 2 examples to see. But question stands, can it actually be used for something real? And in fact, it can. We use it for at work, as it's the first stage of a compiler. And what it does, it parses text into the scripting language. So what you can express in this language is some kind of function composition. This one specifically takes a string and replaces names in the string with the word censored. This is not exactly what we do at work, but it's a good example. So how you do it is the same as before. You have this output ADT, and it allows you to express values, functions, and references, and then we define our grammar as before. But now we do it differently. We actually use this abstract class, and it requires instance of parser operations. Why it's needed, I'll show you a little bit later. But as before, it is composed of a lot of codecs. These are not interesting, they're just character extractions. But this is interesting. And it's interesting by 2 different reasons. The first one is that this is a real application in 6 lines. Well, I didn't show you mapping functions, but they are not interesting, they're trivial. And this real application actually does something useful. Something useful that we can use at work for production. And the second reason that it shows the power of functional programming itself. So here we have these little definitions that we can then compose into bigger definitions. And in fact, if you look how it works, it simply takes this input and maps pieces. For each component maps specific small pieces. And once you start composing them, the amount of input they understand grows as well, until eventually the final program consumes complete input. So the next is really mechanical. you just instantiate parser by giving a type parameter to grammar. That's the codex that we saw before. And now I'll show you another feature that we have. So that's the point of using this abstract class, was to show you that library can do more. So what we have here is, it's the same definition, I just swapped it and compressed it so it will stay on slide. But the problem we're trying to solve, or at least make a step toward the solution, is the fact that comments do not compile. So what we want to do here is we want to get some meaningful documentation out of the program itself. And just to help the library print us something useful, we annotate this codex with simple descriptions. This can be descriptions that is useful for you, like in terms of web service, could be some documentation about meaning of endpoints. Here I just used just synonyms, names. Now the next thing we have is we can use the existing grammar and just instantiate a new instance of it with something that is a context-free grammar printer. But in reality, it just another program that looks at this existing program of codex and translates it differently. It doesn't have print or parse because essentially it doesn't even run anything, but it has show. And this show, if you use it, it gives you something like BNF. That feature was proposed by Alex Konovalov. He suggested it to us some time ago, and we managed to implement it here in a nice way. So the output is essentially some nice printout. And since this feature is available on all codecs you define, you can print all of them. In fact, if you print expression, it will show you how this expression is created. And this corresponds precisely to the definition of this expression. It translates all the codecs defined before in the program into a printout. How is it possible? Well, because everything is a value. The functions you as a user give to a library are values. Codecs are values, and composition of them are values. So what we do is we just use these values differently. In case of parser and printer, we use them to create functions that you can run. And in case of this context-free grammar printer, we only use composition and print out this composition. And Ryan will have something else.
All right, so in conclusion, building parsers with scalaz-parsers is, the intent is to, it's actually a general purpose means for building them. So if let's say you need to parse JSON or XML or commonly well-known format, there are plenty of parsers out there available that would support that. And we would certainly recommend using one of those. However, for specialized parsing needs, maybe it could be even a subset of JSON or XML possibly. This using invertible parsers certainly makes sense. And as far as stack safety, it really depends on the monads that you use. If the monads are stack safe, then you should be fine there. We do have it on, we are considering for a future opportunity actually adding support for generalized stack safety. Now, as far as future work on invertible, on scalaz-parsers, there's opportunity for additional combinators to be added, and that's helpful as we start building more parsers using scalaz-parsers. We would want to have more fine-grained control and allow us to make a wider variety of different types of parsers. And of course, documentation is a big one that we need to add as well, as we've been focusing on the core implementation. Documentation is currently rather lacking in the project. So that's another important one. Performance profiling and optimization. We're definitely going to need to do some performance profiling as well. So that's certainly on the list. And as far as future direction, these are actually a number of design principles that we've actually had since the beginning that are going to become increasingly important. And one of them is abstractions for allowing one to use scalaz-parsers as a part of a greater end-to-end compiler framework. So that means somebody wants to build a full compiler and maybe they want to generate some P code, for example, and actually be able to interpret that. Maybe they're going to write an interpreter or compiling the machine language or something. We want to support that by adding some abstractions that would allow someone to drop in scalaz-parsers into a full compiling solution. And also, another principle that we've actually had since the beginning is, and this hasn't been implemented yet, is separating between the tokenizer and the shaper parsers. And what I mean by that is trying to create a separation of concerns between when you handle the input, well, definition of a tokenizer being where you have input and you want to generate a sequence of tokens, atomic units that are represented by your language. That would be the tokenizer, whereas a shaper parser would take that sequence of tokens and emit an abstract syntax tree. So we want to keep those, we want to support allowing someone to build a parser in those two stages, which is often done for complex languages. And that also, of course, includes the support for how do we represent token and AST types in an abstract way. We have some ideas of how the shape might look like, but that's currently under development. See how that's going to form. And BNF support is something we've been really interested in since the beginning as well, because BNF, Bacchus Norform, that's a very commonly well-known format for representing context-free grammars. And when you're building languages, CFGs are very important, and it'd be nice to have more comprehensive support for that. So yeah, we want you. We liked it. Being an open source project, scalaz-parsers is always looking for people to contribute. So yeah, definitely the journey is just beginning on this project. It's been exciting so far, and there's definitely a lot of future work that we have in the books for it. So yeah, thanks everyone. Anybody have any questions?